The desire to construct artificial life is an ancient human obsession. Long before we had microchips, inventors were forging iron joints and complex clockwork gears, trying to physically build a machine that could replicate human motion and thought. But after the Second World War, the mathematician Alan Turing realized that physical gears weren't necessary. He argued that the newly invented digital computer, a machine built to process numbers, might actually be capable of processing logic, and perhaps even human thought. That theory became a formal academic pursuit in 1956. At a summer conference at Dartmouth College, a small group of scientists gathered to outline a new field of study. They gave it a name: artificial intelligence. This flowchart illustrates the core premise of those early researchers. They believed human reasoning was simply a mechanical process of manipulating symbols. If you could reduce thought to a series of steps, a machine running binary logic could be programmed to simulate it. The invention of the digital computer moved the concept of intelligence out of the biological world and into the realm of mechanical engineering. The U.S. government and defense agencies poured millions of dollars into this new field. In return, prominent researchers confidently promised that a machine with full human-level intelligence would arrive within a single generation. To secure that initial funding, they pointed to concrete early wins. Scientists programmed these massive, room-sized machines to successfully play a decent game of checkers and even mathematically prove basic geometry theorems. Then came programs like ELIZA, an early text chatbot. Users typed in English sentences, and ELIZA spit back structured responses based on basic grammatical rules. People started treating the program like a real therapist. This illusion of comprehension led the lead researchers to make wildly optimistic predictions about the imminent arrival of true thinking machines. But those early successes laid a trap. The scientists had mistaken progress in highly constrained, logical puzzles for progress in general, open-ended human cognition. By the 1970s, the optimism ran out. When early logic programs were tested against the messy, unpredictable real world, they failed to scale. The roadblock is captured by Moravec's paradox. Researchers discovered that high-level mathematics and logic were actually computationally easy. The genuinely difficult tasks were the physical things a toddler does without thinking, like recognizing a face, picking up a block, or simply navigating a cluttered room. The financial fallout was immediate. Governments in the US and UK saw the lack of progress, lost patience, and entirely cut off funding for undirected AI research. To survive, the field pivoted in the 1980s. Scientists abandoned the pursuit of general intelligence entirely. Instead, they built expert systems, software fed with thousands of rigid, specialized rules to perform narrow, large-scale corporate tasks, like diagnosing specific equipment failures. But these systems required incredibly expensive, specialized hardware to run. When cheap, powerful desktop computers flooded the market, the economics broke. The specialized AI hardware industry vanished rapidly, triggering a second devastating freeze in funding. These twin collapses proved a crucial point. Trying to achieve intelligence by hard-coding human knowledge with top-down, rigid logic rules was a definitive dead end. In the 1990s, the field moved away from top-down logic.
Researchers turned back to neural networks, systems of connected nodes modeled after the human brain. As processing hardware experienced an exponential spike, combined with an explosion of internet training data, these networks finally had the computational force needed to become viable. In 1997, an IBM computer named Deep Blue defeated the world chess champion, Garry Kasparov. It proved that sheer brute force computational power could successfully calculate enough variables to overcome human intuition in a highly complex game. But chess is finite. Go is not. So when Google's AlphaGo defeated world Go champion Lee Sedol in 2016, it wasn't relying on rigid brute force. The machine had played millions of games against itself, demonstrating genuine pattern recognition and learning. While public attention focused on board games, this machine learning technology quietly embedded itself everywhere. It became the invisible infrastructure powering your search engine results, advanced medical diagnostics, and global logistics networks. The field had stopped trying to program a human mind from the top down. By building robust pattern recognition systems from the bottom up, the technology actually began to work. Faster, energetic pace. Then, in the 2020s, the field experienced a breakthrough in large language models. These new architectures demonstrated a startling ability to ingest vast amounts of text and then process, predict, and generate human language with high accuracy. To make these raw statistical engines useful, engineers applied a technique called reinforcement learning. They rewarded the models for helpful answers and penalized them for errors, refining them into systems that could safely and reliably hold a conversation. When these chat-based models were open to the public, AI shifted from a hidden enterprise tool optimizing databases into a direct consumer interface used by hundreds of millions of people. Natural language generation crossed a critical psychological threshold. In daily digital conversation, the output from these models became largely indistinguishable from human thought. By 2025, the focus expanded outward. Tech giants and governments initiated massive physical infrastructure investments, highlighted by multi-billion-dollar efforts like the Stargate project, designed to supply the enormous electricity and hardware required to train the next generation of models. This compute power enables the next step, giving these advanced conversational brains a physical body. Complex AI systems are now being integrated into robotics, allowing machines to understand natural language instructions and execute precise tasks in the physical workspace of manufacturing lines and healthcare facilities. The global economic stakes are immense. Competing nations are heavily funding this autonomous physical automation to solve real-world problems, offsetting shrinking workforces and streamlining supply chain bottlenecks. Compare today's autonomous agents with the original Dartmouth Conference in 1956. What began as a purely theoretical discussion about symbol manipulation on chalkboards is now directing physical actions in the real world. The laboratory experiments and high-stakes games of the 20th century have given way to something far more permanent. With hundreds of billions of dollars now flowing into automated factories and global data systems, these tools have moved into the foundation of modern industry.